Hello, my name is Darren Thomas and I am the Director of Educational Research Techniques. In this video, we're going to be taking a look at infinite geometric series. So let's go ahead and get started. Up until this point, we've been dealing with finite series and finite sequences. In other words, there is a clear beginning and an end to whatever we've been looking at so far. So in the past, we might have seen something along the following, where you have the summation k equals 1 to maybe 3 as an example, and then 2k, and so then your numbers will be as follows. So k will be 2 plus 4 plus 6. That's it. There's a clear beginning and an end here. This is an example of a finite sequence, and when you add this up, which is what summation is about, you will get the answer 12, and that is the finite series. Now what we're looking at is infinite sequences, and of course infinite series. So let's take a look at that. So here's an example of an infinite series. And so with an infinite series, you have something that looks along the lines like this. You have your summation sign again, but notice this guy, I'm going to put this in a different color. Notice this guy on top, that's the infinity symbol. It means goes on forever. And then you would have your k, and of course whatever the actual equation is. And so in this particular situation, we go from 1 to infinity. In other words, you continue adding forever and ever and ever. So if I were to write out some of the terms that might be in this one, it would be again 2 plus 4 plus 6 plus 8 plus forever and ever and ever and ever. And in this particular situation, you can tell right here what our R is, or by what I mean our ratio. Our ratio is going to be 2. And so in this particular situation, because we add up forever and ever and ever and ever, and it never stops, there's no end point, there's no boundary. This is an example of not just any kind of infinite series, but an infinite series that has no bound. Another way we can say that is it is not defined. Not defined. And another way that they like to talk about this is that it diverges. I spelled it wrong. Diverges. It never converges to one particular number. That's what's happening here. And so we just go on and on and on, adding, and we never stop adding. So it's an example of an infinite series that diverges. It is not defined. It has no boundary on it. There's no upper limit on it. And of course, we can if we have series that are not defined, that have no boundary, that diverge, we can also have the opposite, things that do have a boundary, things that are defined, and things that converge. And the catch for convergence is when the R, now watch this carefully, R has to be greater than -1 but less than +1. Any R or any ratio between these two numbers is going to be defined, is going to have a boundary, whatever word you want to use, and it's going to converge. Whatever term you want to use, that's what matters here. So let me give you an example of this. Now let's say I have the following. Of course, I have my summation sign again, like so. And of course, I go to infinity. My k starts at 1. And I'm going to have 1 over 5k. Now remember, this 1 over 5 here, this guy right here, this is my ratio. And 1 over 5, it is definitely greater than -1, but 1 over 5 is also less than +1. So we know for a fact that this converges. In other words, as we create each term in this infinite sequence, they'll get closer and closer to 0, and we can eventually sum them up. That's the rationale behind this. So if I were to just give you an example of some of the terms in this, it would be 1 over 5 plus 1 over 25 plus 1 over 25, let's see here, and 25 times 5, 125, excuse me, like so, all the way on, dot, whatever. And you can see each time that the number is getting smaller and smaller and has less and less influence on the final answer. That is what's happening here. Now, what we're going to do now is we're going to look at two examples and see if we can figure out if they are defined or not defined, if they converge or if they diverge, etc. So let's take a look at the first one here. So here are the numbers. We're going to have 24 plus -12 plus 6 plus negative 3, and then we're going to just put in our dot dot dots after that. We know it's infinite. Now, to find out, first we have to figure out what our ratio is. We have to figure out our R. And R can always be figured out with this little equation right here, this little formula right here, A2 over A1, or any two adjacent terms. So with this in mind, my A2 is going to be 12 over 24. This gives me an answer of negative 1/2. Now, remember, we already know that negative 1 R 1. And so negative 1/2, it is definitely greater than negative 1, but it's also less than positive 1. So it looks like this is going to definitely converge. It's going to be defined. And if we really wanted to write this out, if we were like, bored one day, it will look something like this. Start with K equals 1. Start like this, and then it'd be 1/2 times, it'd be negative 1/2, excuse me, negative 1/2 times K. That's what's happening there. And so you can see that's how you would write that out if you want to put it in summation notation. Let's do one more. So this time, instead of having the terms, we're going to start with the summation notation formula, if you will. So I got the following. I start with K equals 1. I have infinity right here, and then I have 7K. All right. So this one, again, we just go back to our original plan here, negative 1, R, 1. Well, this 7 is definitely, because, this is the ratio right here, nothing to calculate. 7 is definitely greater than 1. So we can definitely say that this does not, this is not defined. This does not have an upper boundary. This does not converge. In other words, it diverges. And so you can see if we start plugging numbers in, we start with 7, then we have 14, then we have 21, then we have 28, on and on and on. And see, you can see here that each number has more and more influence on the final answer. This is the opposite of when it was diverging, when each successive number has less and less influence on the final answer. So we'll just be adding forever and ever and ever. So again, this is divergence, something along those lines. All right, so let's go ahead and review what we talked about in this particular video, and then we will wrap things up. So in this video, we reviewed about the difference between a sequence and a series. So a sequence is a collection of numbers. A series is a summation of a sequence. And so far, we've been doing finite sequences and finite series where there's a clear beginning and end point. However, life is not always that simple. Sometimes we have things called infinite sequences, which, in other words, this number at the top of the summation sign is an infinity symbol, and it goes on and on. Now, when your R is greater than negative 1 but less than positive 1, you have what we call something that can converge. Something that where you start to add it up, it'll eventually have some sort of a stopping point. However, whenever your R violates this rule right here at the top, it will diverge. It will not be defined. It will not have a boundary on it. And so again, we did two examples of this. Here's our first example, where first we had to find the ratio, which is just taking two consecutive terms and just finding the ratio between the two, and then plug it in. And then whatever this answer is right here, we compare it to our little formula of negative 1 is less than R, negative 1 is less than R is less than 1. We plug it in and see where it lies at, and that will tell us if our particular series will converge or diverge. And then we also had a second example right here. In this example, our R is clearly bigger than 1, clearly bigger than negative 1, and so this will diverge. It'll never come to an end. So I hope this video was useful for you and you were able to understand what we talked about here. My name is Darren Thomas. I am the Director of Educational Research Techniques. Take care.